Okay, welcome to a special space science webinar of the New Mexico Museum of Natural History and Science. We are so pleased that you've chosen to spend some of your afternoon time with us for this great event. We're very proud to be the only museum nationally, except for the Smithsonian Air and Space, to have been involved in 2 Mars rover missions, including the current Perseverance mission. And today we're going to be hearing about that really amazing, exciting mission. First off, let me tell you that the chat and raise hands have both been disabled. If you have questions during the lecture, please enter them into the Q&A box, and they'll be answered either in writing or verbally at the end of the session. You will receive of this webinar in about 2 weeks at the email by which you registered. And before we start, we want to tell you about a couple of exciting things that you might look out for. On October 26th, the museum will be offering a virtual tour of the bees exhibit, 4 p.m. October 26th. So check the website for more information about that. In addition, some of you may know that the museum has had limited days, limited hours. We just, for the period between this coming Wednesday and the end of Balloon Fiesta, so September 29th to October 10th, the museum will be back 7 days a week, still 10 a.m. to 4 p.m., but all 7 days a week for that time period. And then, unfortunately, we will have to go back to just Wednesday through Sunday. So take advantage of it while we're open 7 days a week. So the Perseverance mission is pretty exciting already, and we're going to hear from one of the scientists involved. Dr. Larry Crumpler is museum research curator here at our museum and member of the Perseverance Rover mission science team. He previously was on the development team for the Ingenuity Helicopter, the Mars Exploration Rover science team, the Mars Odyssey Gamma Ray Spectrometer science team, the Mars Reconnaissance Orbiter High Resolution Camera science team. And on the Perseverance mission, he's responsible for geologic context mapping of the terrain. Excitingly, he has a book coming out at the end of this year, and we are planning a book signing event. It will be available through NatureWorks. So keep an eye on the museum website for more information about that. But it does look like tentatively it will be December 9th. Okay, so without more ado, I would like to introduce Dr. Larry Crumpler and his talk, Exploring a New World, the First 200 Days on Mars with Perseverance and Ingenuity. Larry.
Okay, I'll take it away. And so, welcome to Mars. This is Sol 215 since we landed. It's currently a few minutes past 7 p.m. at Perseverance landing site. And what I'm going to do today is just run through a few of the things that we've been doing since the landing back in February the 19th. And so it's going to be kind of a really quick tour, and I may skip over a few things fairly fast, so just jot down a note and ask a question about it if I don't cover it adequately. But I hope to give you at least a kind of an overview of some of the things we've been doing. Obviously, there's been many things. There are many science team members, and there's just so many different investigations going on. I will be giving you sort of my biased view of what we've been doing. Okay, so, in many ways, exploring Mars is like the great natural history exploration missions of over a century ago, or even going further back, the exploration of the New World. In this case, we're doing a new world, but we are doing it in the real sense rather than in the literal, in the figurative sense. We're actually on a new world. We're marching out across the terrain. We're seeing things that no one has ever seen. We're going places where no one has ever been. So we're really a band of explorers roving over the surface of Mars. Except for this mission, we're actually not only just traveling on the ground, but we're obviously traveling in the air. So let me just give you a little background on how we got to this point. So, over the years since the beginning of the space age, our view of Mars essentially changed from the view over there on the right, which were telescopic views of Mars in which we could see all sorts of strange blotches and markings. And in fact, just before the first spacecraft arrived, these blotches and markings were actually compiled into maps. This was the official map going into the first flyby mission in the early 60s. And then subsequently, of course, our view of Mars has changed to a planet that's totally different from that view. In fact, Mars has been doing these little bait and switches to us over the past 50 years, in which, we think we're seeing one thing, but then it shows us what it's really trying to show you. In this case, we saw these markings and we thought those must mean something, and it turns out they mean absolutely nothing. They're just dark markings on the surface, and underneath all of this is an actual terrain which is actually quite exciting and geologically active in many ways. And then subsequently, over the past 30 years, we've sent many spacecraft to Mars and learned even more details about it. So we've gotten to the point now where we're looking down from orbit with cameras that are essentially taking images that are like aerial photographs, so we can see things at the human scale on the surface and really get down to the nitty-gritty of the geology. And of course, we've also been roving on the surface. So now we're actually ground pounding, actually walking out across the terrain. So in that process, we've learned new questions, and even more importantly, the things that we need to explore to even understand Mars a lot better. So, of course, how we got here were all of these missions, these orbiters, beginning with the Mariner 4 mission in 1965, flew by Mars, and we get our first up-close views, sort of. They were kind of grainy images, and they unfortunately looked at a part of Mars that was quite cratered. So we started out with a sense that Mars was a dead place, but then subsequently we sent missions like Viking, with 2 orbiters and 2 landers, which actually went down to the surface. We had our first successful landing on the surface of Mars. And then there was a 20-year hiatus between the mid-70s and the late 90s, both the orbiters and the landers. And during that time, we basically learned to analyze all of the Viking data and ask questions that these later orbiters and landers and rovers could ask. So in late 90s, we sent the Sojourner rover, which was the little microwave-sized rover, onto the surface of Mars, which lasted for about 90 Martian days. And then, of course, in the early 2000s and 2004, we landed Spirit and Opportunity on Mars. where we started to rove across the surface of Mars and see it as you and I would see it walking across the surface of Mars. Subsequently, we've sent several other orbiters with increasingly more sophisticated instruments and more sophisticated landers and rovers, including the Phoenix lander at the high latitudes of Mars in the mid 2000s. And then, of course, in 2011, landing in 2012 was the Curiosity rover that is currently operating on the surface of Mars, and it's similar in scale to Perseverance. And then there was the InSight lander, which recently observed a magnitude 4.2 earthquake on Mars. And coming up to today, when we have the Perseverance mission, and its goal really is to collect samples that will eventually be returned by a Mars sample return mission later in this decade. Okay, so a little bit about the mission. Again, as I said, the important goal of this mission is the collection of some samples that we will return. So we are tasked with collecting samples of known geologic context and caching them, that is, placing them in collections on the surface for eventual retrieval by a later rover. And anytime you sample rocks in the field, you want to know something about where they came from, the geologic context. And so we're also tasked with really trying to understand the geology of the rocks and the landscape around the rover, and in particular of the places where we actually collect those samples. And so that's a big part of what I do on this mission. And of course, it all comes down to what we're really trying to do is get to this question of astrobiology. That is, biology beyond the Earth, in this case on Mars. And we're looking for all the signs that were suitable for life, look for signs on the rocks themselves. So in a sense, this is kind of a fossil collecting mission. If there are indeed preserved microbes, hopefully we'll stumble across them. And then, of course, prepare for future missions, including human missions to Mars, with testing several different technologies. About the rover itself, of course, we have a high-resolution camera on the top called Mastcam Z. We just sometimes refer to it as Z-Cam. And that takes these wonderful color images at high resolution. It has a zoomable function, so we can really zoom into things in the distance. So it's otherwise very similar to the Mastcam that was on Curiosity, but we can zoom in at great distance with like a 120 millimeter lens. Then we have the SuperCam, which is similar to the ChemCam on Curiosity, but with several upgrades. This, of course, was the instrument that's being run by Roger Wiens up at Los Alamos National Labs. And it has all sorts of capabilities in addition to the laser, shooting at rocks that actually analyzes the composition of the rocks from a distance of 7 or 8 meters around the rover. It also has the capability to look off in the distance with what amounts to a small telescope that can allow us to see details in great distance, many kilometers away. Also, it has a camera, a microphone that we've used to listen to rover sounds and helicopter sounds and things like that. It's also used for understanding the nature of the rocks and other characteristics, but that is a cram-packed instrument in itself with all sorts of capabilities. Then out on the end of the arm are several instruments. One is called Pixel. Pixel is an X-ray spectrometer, which is similar to one we've seen on previous missions. It basically looks at rocks with irradiating them with X-rays, and you can understand the elemental composition and thereby understand what the rocks are actually made out of. Except this one actually has the ability to do it at micro spot scale. So we can analyze individual grains. And we do that by using this instrument, Sherlock, which is actually two investigations. One is Watson, which is our microscopic imager. And it basically allows you to look at rocks up close in extreme detail, as well as being able to hold it out in front of the rover and take selfies and things like that and other interesting landscape images. And also part of that instrument is an ultraviolet spectrometer, which is good at detecting things, especially organic compounds. So that's going to be very useful for looking at a sample that we believe might have some microbial fossils or something, and understanding whether there are in fact organic compounds present. And then finally, there are a couple of other instruments. There's META, which is the weather station, which does a variety of things, temperature, pressure, but also looks upward at the sky. You can observe clouds and atmospheric dust and so on. And then on the back of the rover, actually mounted underneath, is an instrument called Rimfax, which is essentially a ground penetrating radar, much like the radar we use here on the Earth for looking for buried pipes. Geologists, however, use it a lot for understanding the shallow substrate beneath your feet. And on Mars, it works particularly well because the dry soils allow you to look at depths much greater than you can even here on the Earth, up to 30 meters or more. It's a very important instrument. And then, of course, there's a couple of technology demonstrations. One is the rover itself has considerable autonomous capability, and we'll see an example of that in operation later in this presentation. And so that allows it to drive great distances without a lot of input from the Earth. Then there's an instrument called MOXIE, which is good at generating oxygen from the Martian atmosphere. It'll be very important for future human missions, and we've already tested that, and it works quite well. And of course, the last but not least is the Ingenuity Helicopter, which is essentially a technology demonstration of their ability to fly aerial vehicles on Mars. And of course, it's succeeded wonderfully. And we'll spend a lot of time with Ingenuity in this presentation, looking at some of its doings on the surface of Mars since we deployed it. Okay, getting back to the sample return. So this is how that's supposed to work. Perseverance basically collects samples, stores them on board, and then in a few select locations along its traverse, puts them out on the surface, just lays them out on the ground. They're in sealed tubes, and because they're little cores, and they're completely sealed against the environment, so they're laying out there. And then later in this decade, a rover will go and retrieve those, bring them to an ascent rocket, which rendezvous with an orbital vehicle and Earth return vehicle, and they come back to Earth. And here's what one of those sample tubes looks like. We have 38 samples that we can collect, and there may be multiple cache sites along the traverse. And when we get these back, this may look small, but that's more than enough for the sophisticated instruments and laboratories here on the Earth to understand things that we've never really been able to understand before, because now these will be rocks that have complete documentation and curation with respect to the geologic context. So where did we land on Mars? This is the Eastern Hemisphere, and it landed in the northwest corner of this area called Isidis Planitia, and in a place called Jezreel Crater, and we'll look at that in detail in a second. But there are a couple of other landing sites on this hemisphere. One is, of course, Curiosity rover, which landed in Gale Crater in 2012, still operating and still climbing a mountain in the middle of the crater. Then there's InSight lander, the one that is looking at Mars quakes. Just to the north, it's already seen several earthquakes from this, one of the youngest volcanic areas on Mars, in an area of Cerberus fossae. And another dot here is the Chinese lander and rover Zhurong, and it's operating. It landed a few weeks after we did on the surface of Mars early this spring. And speaking of which, here's a quick view of the latest image from Zhurong. This is a panorama taken down here at the end of this several hundred meter long traverse. Zooming in on this area, you can see a typical Martian scene, dunes, lots of soil or regolith. Zhurong, of course, is a solar-powered rover, very similar to Spirit and Opportunity, right down to the little calibration target, which looks like a duplicate of one that we had on Spirit and Opportunity. So let's go back and look at where we are on the surface here in Perseverance site in Jezreel Crater on the northwest edge of Isla Polynesia. Why did we go there? Well, here's a view of it. It's a crater. It's about 30 miles across, and it has some very interesting features we'll look at in a second. Most important of which is a river that came into it, and so it was a crater that was filled with a lake at one time. And during that lake presence, this river actually deposited a little delta, which is what happens when water enters a large body of water and it slows down and dumps all of the sediments that it's carrying and load. We landed out here just off the delta. This box is the same size as this box here, so you can see this is Albuquerque. Here's Washington, D.C. at the same scale. So it's like we landed up here, say, near the university, and we're basically going to be driving down here somewhere in the North Valley. Zooming in a little bit, again, here's our image of Jezreel Crater. Here's the box we were looking at on the right. So here's what happened. A river came in, dumped the delta, and the delta basically was this broad fan-shaped feature that over the millennia after the lake dried up, eroded back into this nice escarpment. And then other things happened on the crater floor. We believe a lot of these are lava flows and other things, as well as lakeshore deposits up here in the on the left, which are known to contain carbonates and things like that. So these are all just excellent environments for exploring, for doing basically a fossil collecting trip, if there are any. So here's where we landed. And of course, I won't go through the details. You've probably seen all of the images of the landing. We had cameras taking movies, looking down from the lander and looking up from the rover at the lander. The rover was unspooled on cables from the lander to get the rockets away from the surface so it wouldn't kick up so much dust. And basically, once the job was done and it touched down, these cables were cut and the lander flew off. And it landed us in a beautiful, flat, boring place here in the floor of the crater. Off in the distance, you can see the edge of the delta. And there's the rim of Jezreel Crater. In the foreground, these are blast marks on the rockets. There's a similar set of blast marks over on the right side of the rover. You can see where we blew dust off of the surface. So once we landed, we had to set up all of our instruments, get things going. Very complex rover. It takes a lot of software that has to be loaded up, and some of the flight software that got us there was taken off, and all sorts of things. So it took us about 60 sols, but also during that time, we deployed the helicopter Ingenuity onto the surface. And this is just a view looking back. You can see some of the features that you can see from that orbital view. There's the delta, and so there it is in the background. So there's Ingenuity after we just deployed it to the surface. Again, the crater rim in the background. And this was such an epic occasion that we took a little selfie. The rover, like a proud parent, looking down at this little buddy that it deposited on the surface. And we've been kind of playing tag along the surface for the past 200 sols. The surface here, you can see our blast marks over there again where we landed, so we've moved away from that. The surface here has the strange pattern of what we call pavers. They're kind of polygonal little blocks that are surrounded by dirt. It's simply rocks that have fractured, large rock mass that gets fractured into these polygons, and now they're being exposed intermittently with dust. So anyway, the helicopter actually underwent a series of successful test flights, flights 1 through 4. We actually flew and ever-expanding arcs, and we launched from an area way over here, 60 meters away. We drove away from the helicopter because we didn't want it to go haywire in its first test and crash into the rover and terminate the mission. So anyway, this is a NavCam view from 60 meters away looking back. And you see it looks far away, but nav cams are kind of like wide angle lenses. They make things look far away. And but nonetheless, we have the mass cam or a Z cam that can zoom in. And so here's the helicopter actually sitting on the surface out there, awaiting its first flight in this case. This was Sol 55. So the first flight, we took lots of images. With the third flight, we took these beautiful color images looking down at the landing site and the surroundings. As we flew over, here are those strange polygonal pavers. Here's where it took off from. You can see the helicopter shadow here. Here's a footpad that appears in most of these color camera images. And during this flight, there was the Rovers parked out over here. And so we actually got a picture of the Rover over there on the horizon. These are sort of fisheye lenses, so it makes the horizon look curved. It's actually quite flat. Anyway, you can zoom in on that, and there's Perseverance sitting out there watching with the camera pointing, taking movies of the flights as it progressed. In this case, the rover is actually facing away from you. This is the rear end of the rover, so it's kind of looking over its shoulder. So altogether, we've seen the rover from the air about 5 times in subsequent flights. Now here's the fifth flight. We actually flew to the south and landed in a place that it had never landed before. And so here it is actually flying out. And here's a movie we captured of it. You can see that here it is. We actually flew on Mars. You can actually see it taking place. And it's doing this little investigation of its potential landing site. And now it's coming in for a landing. And in the high resolution camera view, there's actually a dust devil going on in the background back here, which is another common characteristic of this Jezreel Crater landing site. Crater rim in the background, crater floor in the foreground. Okay, so basically at that point, we were still back up here near the landing site. And we needed to get over here to the delta, but this area is too rough to cross, so we actually need to go around it. Turns out that the best way is going this way, but in order to understand everything out here, we had to go to the south because we want to get to this old rough terrain, which is really older than even this terrain that we're sitting on. And this is older even than the delta. So we basically undertook this traverse going south, trying to get over to this point where we could actually move into this older geologic unit and look at it. So that's what we've been doing literally for the past 200 sols. But meanwhile, Ingenuity's been hopping along. These little green dots are all of its landing sites. So what's been happening is as we drive along, it's basically been following us. And we drive up and drive past it. And so we can see it sitting off there in the distance. Here's images on different sols as we drove along, and we would drive. Ingenuity was far away, and then we would finally get to where it had already landed. And sure enough, there it was sitting there. And this went on until about Sol 129. And then basically it flew pretty far away. And we didn't see it again until Sol 184, just a few weeks ago. And so here it is sitting out there waiting. And you can almost hear it jeering at us. Like, hey, slowpoke, what are you doing? I've been sitting here for sols waiting for you. I mean, it's just moving in front of us and doing its job, which is basically to do aerial reconnaissance of the path ahead. So during those flights, it's been taking these beautiful aerial photos. You've seen some of the color images. We'll look at a couple more. But it's also been taking these downward-looking nav cam images, which can be turned actually into movies, but they're long strips of these black and white images, as well as the beautiful color images. So what I'm going to do next is move down to this location where it took off and flew all the way across the Badlands to get to the other side, where it's sitting currently way out here. And meanwhile, we drove around the Badlands to get to where it was. And so here's where we were sitting at this location. We drove away from that location before the helicopter flew, but it looked down on where we had been, and I've placed a model of the rover in the scene here so you can see the scale of the images taken by a helicopter looking down. And you can see again these paver-like rocks. Here you can see our tracks. And so it flew across here, flew out, and did a long flight over here. So next I'm going to show a short clip of a movie from these nav cams, which shows it taking off from this location, flying over these tracks, and then passing over, this is a big escarpment, passing over this escarpment, and then embarking on a great journey across the Badlands to land over here, and again in a place that we had never seen before. So it has considerable autonomy in choosing its own site. So here it is taking off. So it's gaining altitude. There's our rover tracks coming into view. And now it's going to start on its journey, passing over where we had previously been parked, passing over those paver-like rocks. And now it comes to the edge of this big escarpment over here. So this is the edge of the escarpment. So it's like it's stopping and saying, oh, I don't know, this is pretty scary, but here I go. So it took off and flew all the way across this terrain down to the south here. And this goes on for a couple of minutes, basically flying over dunes and scattered outcrops and whatnot. So let me just move to the next scene, which is the color images that it took while it was flying. And so this is one of those, looking out across the Badlands. This is where it was flying to, way on the other side of this Badlands that we call Seta. And it is, at an altitude of about 20 meters. There's the rim of Jezreel Crater. There's part of the delta out here. And so this is the type of view that we have as we're flying along. There's the footpad again. Then when it got to the other side, it did some flights. And then when we had come all the way down to this point, it was over here, and it did this flight out to the northwest. And when it took off, it did an image looking back towards the east here along the edge of this escarpment, which is right here. We were sitting down here, and you can actually see the rover way up there out in the distance. And you can zoom into that. There's the rover again. Looking at an outcrop, and this is where we actually were doing our first sampling opportunity. Okay, so that's enough for the helicopter for now. Let's get back to the rover. Here's some of the things we've been doing with the rover. Of course, it has the telephoto lens on the Z-cam, and so here's a view of that fragment of the delta out in the distance, which is a good kilometer away. And you can see all sorts of details in this. And all of the sedimentologists on the mission are, of course, really drooling over some of these images. This looks like an image that you might take out in the Rio Puerco here in New Mexico. Beautiful layering, cross beds, all sorts of other details. Supercam actually did a telescopic image of this outcrop, and it's even more spectacular up close. So that's one of the things. So speaking of Supercam, so here's a view of what Supercam can do. This is when we were back close to the landing site. Supercam looked at the edge of the delta and looking at these outcrops out there. And so this is literally, the quality of image that Supercam is able to acquire from over a kilometer away, looking at the top of the delta. Beautiful high resolution. You can see a channel exposed in cross section here, lots of blocks. It's actually quite blocky for a delta, so we think this is a later debris flow or something. But anyway, that's the sort of images we've been taking. Also, every time we stop, we take a panorama, the images have been photobombed by dust devils. Dust devils are really prevalent in the floor of Jezreel Crater, and every afternoon about 2 o'clock, there's dust devils galore. In fact, there's several going on in this image. If you look in the background, you can see some faint ones. So it's a really dust devil ridden place. So just as a captive audience, you have to see what I've been doing. And of course, my investigations is in situ or field geologic mapping, or shortened for GXM, of the rover's traverse. Basically mapping the geology as seen from the perspective of the rover as we drive along. And The way I do this is by the same way you do it here on the Earth when we're out in the field mapping geologically. You look at the rocks at your feet and you look off to either side and you identify those rocks in your surroundings and you can map them out in whatever base map you're using, air photo or topographic map. And of course, we can do that because we have these high resolution images all around the rover, as well as things like SuperCam and Zcam. And so we have all sorts of instruments for getting an even better handle on what some of the things around us are. And I've laid it out in a series of levels, which are decreasing resolution with distance. So whenever you look at a particular level, you know what the quality of the mapping in that level is. And so the way the mapping works is, here's a nav cam, and here's some of our pavers again. This is back near the landing site. So you can map out the different rocks that we look at our feet. We investigated these, analyzed them, and so you can see them in the surroundings. You can map them out and the intervening areas of soil. And then you can map out pretty far out because these are all really high resolution images. And then if that's not good enough, we can look at things in the far distance with Zcam and zoom in on outcrop. In this case, it looks like a basaltic outcrop, very similar to anything you might see here in New Mexico. Beautiful, massive, dark basaltic lava flows with vesicles or gas bubbles. And these, in this case, seem to be sitting on top of these pavers everywhere we've seen since we landed. And so we're trying to get a handle on what that really means. And then the way the mapping, of course, works is we have these nav cams, which are in stereo, so we can build 3D models, which we overlay onto the landscape. We can put that on top of our orbital image, which is in the background here. So we have a beautiful overhead view of the landing site. Now we also know the geology around us, so you can start mapping it out at various levels of quality out to the distance around the rover. So this is how the GXM field geologic mapping works. And so I've kept track of the geology all along the traverse. And so here's a map showing all of the geologic mapping that's taken place so far along the traverse as we moved out towards the south. So getting back to the fun pictures though, here's a view of the Sol 110 NavCam image. Here you can see the Jezreel Crater Delta again and the rim of Jezreel Crater. Lots of soil and dunes here, but we were, in this case, this little hill, rocky hill, is actually the rim of a fairly large impact crater that we were driving past. And we can zoom in on those rocks with their Zcam. And of course, craters are good at excavating things, so they're good for like seeing what's underneath the surface. And so in this case, looks like we have a good exposure of some of those dark basaltic rocks that we saw back closer to the landing site. So we know that those rocks are underneath our feet. They're just not always visible. But beautiful blocks, and there's all sorts of things going on in these. But there's another rock that was sitting on the rim of this crater that we got an image of, and it shows some really interesting textures. It looks like it's a block of lava flow. Here are some of the surface textures you'll see on a typical lava flow, gas bubbles or vesicles on the inside and the cross section. So it's just literally been tossed up and thrown out on the surface, and it's a preserved sample of the surface texture of a lava flow on Mars. And this looks just like something you would see if you went out to the Petroglyph National Monument and you know what you're looking for. You can see this sort of thing in miscellaneous blocks out there. So moving further along, so Sol 124, this is just the sample view of what things look like. Here's the escarpment that's immediately to our west as we were driving along the edge of that escarpment. So you can see the rocks here. And so with Zcam, we can zoom in. And so here's one of those blocks. Again, looks like a beautiful basalt with all sorts of gas bubbles or vesicles. And you can see here that the escarpment is basically like any escarpment here in New Mexico where you've got it capped with basalt. The escarpment moves backwards, gets eroded backwards, and the rocks kind of cantilever and tilt over into the slope. So another example of, sort of the details. And then way out here in that Badlands are some beautiful layered terrain. And this is what we really are trying to understand before we get on with the rest of the mission. Just a quick view of what you can see from the ground. So here's a view from Sol 136 when we were sitting here. Here's a model of the rover. This is our orbital image, and you can see these paverish looking rocks. And so you can kind of correlate some of the things you're seeing here with what you're seeing down here. First of all, everything over here is out of the field of view. The limit of your view right here on the local horizon is right here. So there's dunes and more really strange blocky rocks, but down here there are pavers. So we're down here off of this escarpment and looking at these rocks, which again are our basaltic rocks. And again, they're sitting on top of our pavers in this location. And you can see things like, for instance, this dark area right here is this zone right here. This polygon here is this polygon right here. Then the one next to it is this one, and so on. So that gives you an idea of kind of, how we kind of feel our way across the surface of Mars. Moving further along, we are still sitting on those polygons when we came down to this location, which looks very similar to the last slide. Again, our basalt sitting off in the distance, and here are the polygons. And so finally, at this point in the mission, we got the capability to actually do coring and sampling online. Again, a complex mission, a lot of things have to happen to validate some of these instruments and getting them going. And so we just selected to try to understand these rocks. They're very granular looking, very strange rocks. And so we elected to sample this location. So first we did a grind on it to basically clean off the surface of the weathered outside, but that leaves behind a lot of dust. So we have on board a little tool that blows the dust off. It's a little nitrogen gas puff that blows the dust off. And here's that in action. So here's the grind, and there's the dust being blown off with the gas dust. So then you can zoom in to this freshly cleaned surface and see what the rock looks like, and here it is. So here's the overhead view from the GXM map of the rock that's just sitting in front of us. Again, a typical paver. And the rock itself is, it's got these holes in it, again, probably vesicles, and lots of, it's fairly coarse, granular rock. Many of us believe these are igneous rocks, not sediments, but there's still some debate about that. And there's all sorts of details that you don't see in a nice fresh rock normally here on the Earth, including lots of staining of the surroundings of minerals. And some of these white spots aren't feldspar as they would be on the Earth, but a lot of them turn out to be some sort of fillings for vugs, maybe sulfates. Some of them are feldspar, and then there's lots of pyroxene and other minerals typical of basaltic rocks. In fact, Pixel did an analysis of this rock, and it was in class with typical Martian basaltic rocks. So then we elected to do this first coring activity. So here's the drill. We checked it out to make sure the drill's working fine. So here's a little movie of it running in preparation for applying to the surface. So this actually has a coring bit with the sample actually being collected inside this tube that can then be extracted and stored on board the rovers. So we did that coring activity, and so here's the results. A great pile of tailings around the drill hole. It's very extensive. It looks like a little cinder cone practically. And so we peered into the hole, and yep, something was extracted. But when we looked at the sample tube, we held the sample tube up to the camera, looked at it, it was empty. And it was like, what the heck's that all about? Where did the sample go? We looked all around just in case it fell out of the tube or something. But actually, we think what happened was the sample was just pulverized and turned into these tailings during the drilling operation. And so it turns out to be a rock that just isn't coherent, doesn't withstand drilling and coring. So, but then there are alien astronaut theorists who believe that it was aliens. And of course, you don't know, therefore, aliens, right? But really, the reality is the rock was probably quite rotten. That is, on Earth, when you get a rock that's really deeply weathered. Here's an example of that same rock type back near the landing site. You can see these polygons actually have sort of a weathering rind around the outside. They're quite granular. They're falling apart into this types of granular material that here on the Earth, when we see it, we call it grus. Here's an example from western New Mexico, basalt in this case, that is undergoing similar weathering along joint faces or fracture faces, turning into these sort of spherical shells that are crumbling into all of this crumbly debris. And perhaps a more familiar example of that process is the weathering of the Sandia granite. When you go out, the Sandias, a lot of times you'll see outcrops that look like nice granite, but they're very gritty. You can rub your hand across them and rub off grit. Simply the rock is very deeply weathered, and when that weather coat comes off, it results in these roundish blocks or tours, and then lots of gritty debris or grus that is surrounding the outcrops. So it's very poorly indurated rock. And just like the Sandia granite doesn't make good gravestones, that same type of rock is really very poor. Here on the Earth, we sometimes refer to it as saprolite, very familiar to people in the southeastern United States, where a lot of the granite outcrops really look like a sandstone. They're just so soft and totally rotten from deep weathering. So that was back here where we did our first sampling, and as we tried to analyze what to do about that and get our first sample, we continued driving along the escarpment here. So there's a big drop off here down to a low spot. These are our badlands here. Here are some of our basaltic looking rocks up here. You can see our paverish rocks here. And I haven't talked too much about Rimfax up to this point, but it's been taking a continuous ground penetrating view of the subsurface of Mars as we drive along. And so here's a little sample of that. None of this has been really released to the public yet, so I don't want to spend a lot of time on this, but I just wanted to show you some of the typical results from the radar, ground penetrating radar, Rimfax. Here's the profile going from this location here all the way to location up here, and it's along this drive here. And what's interesting is as we drive along here, you can actually see dipping reflectors, as they're called in the business. Means something that's a little bit denser, so it's probably layers in the rock that are actually dipping off to the southeast in this case. And there are other images that have even more detail. So this is truly a wonderful instrument. We're looking down to 25 meters below the surface. So you'd love to have this in the field on the Earth. But here on the Earth, with all the moisture content of soils, you're lucky to get down a few meters at best. But, this is just wonderful. And stay tuned for more information coming from Rimfax. So I just wanted to show you a typical outcrop and a couple of other things before we wrap up here. So as we continued along, we decided to look at some of the rocks on the escarpment here because we had a beautiful cross section. So we drove along and parked next to the outcrop here, and here's the escarpment edge. And the rocks there are tilted like 10 degrees to the south west. So it's kind of an interesting uplift or something has happened along the margins of those badlands. And so anyway, when we pulled up to the outcrop, here's the view of that outcrop. So you can see again our very weathered, grusy rock mass, and capped by our friend the basaltic cap rocks. And there's some sort of contact through here, but it seems to be gradational. We're still trying to understand that. Also, interestingly, you can see where this little outcrop here seems to be displaced, and it seems to be displaced along a fault, which is this one right here. So it looks like there was a little slump, and so some of the outcrop moved down along the escarpment here. So anyway, that's kind of a view that we have as we drive along and try to understand these things. So we decided maybe this basaltic cap rock was really the rock we wanted to try to sample. It looks more competent and durable. So we drove along the escarpment further to the northwest and then drove up onto the cap rock. And so here's the geologic context map view of our parking location on top of the cap rock, and the red blobs here are all exposures of that basaltic cap rock. So we pulled up to a rock that we thought looked very nice and solid, and did a series of experiments. We did a grind on it and investigated it, did analysis, and then we cored it in 2 places and sampled it, and they were successful. And here's the results. It was such an epic event again that we took a selfie showing our 2 beautiful holes that we drilled in the rock. We looked in the sample tube this time, and there was a beautiful sample sitting in the sample tube. You can see a lot of the similar things that we saw actually down in that first abraded site. A lot of grains, a lot of sulfate vugs, but a lot of minerals, a lot of staining. So this is a sample that's now in the tube. Here's the tube closed up. It's got its sample number, and the sample was retrieved by the rover, stored on board, and now we're going to carry this along and collect a few more samples and eventually put those on the surface for the return in the future. So this is kind of what we're really tasked with doing, collecting samples. So we're in a race to get to the turnaround point out there in the Badlands. And so we started driving, and we're eventually driving out into the Badlands out here. Here's the escarpment again. And so that's where we did that first successful sample up here in these basaltic cap rocks. But it turns out we needed to come up here in order to find a place to really safely enter the Badlands. So we had to do a number of drives, and we're kind of in a rush because we don't want to spend all our time out here on the crater floor. So we wanted to get our look at the Badlands over with and then get on our way to the Delta. So we're driving fast. So here's where we use this wonderful new capability of the rover called AutoNav, which the rover actually, we tell it, hey, we want to go over here. So you start here, go for it. And so it drives itself, avoiding obstacles and getting there, identifying that location and stopping. And so in the next view, we'll look at a movie taken as we drive from this location out to our stopping point out here. So this is the rover driving itself for over 165 meters over the surface of Mars along this escarpment. Okay, there we go. So it's driving along, it's avoiding these rocks. It's saying, oh, stay away from that. Stay away from these, move over here, oh, back over here, oh, yep, go over here. So it's driving along, working its way towards the final location way up here. And as it gets closer, it checks its location. There it is. So that was a typical AutoNav drive. So with that, we can, unfortunately, drive great distance. Unfortunately, I say, because that means my geologic context map gets broken into these relatively widely spaced map zones sometimes, but at least it allows us to cover lots of ground. So subsequently, we've gone over across the escarpment down into our current location out here in the Seta Badlands. And so that's been happening over the past couple of weeks. And just a couple of days ago, we pulled up to the Sol 210 location out here. We've already looked at a couple of rocks here with abrasion and trying to understand them. So here's where we're sitting right now And here's a view of that location. There's the escarpment that we were driving along. So here we are sitting looking at some of the rocks out there in the Badlands, lots of dunes, very treacherous terrain. Zooming in on some of these outcrops here, this is a view from Zcam. Very interesting rocks, very fine grain, very finely bedded or layered. And many of us believe these are probably, most likely, volcanic ash. There's lots of volcanic ash on Mars. And so that's what we are suspecting. But then, of course, there's a lot of sedimentologists who study sediments on the mission. And they, of course, think these are probably fluvial sediments or something. So we're, kind of looking at these rocks carefully to get a handle on all the field characteristics. So that's where we're sitting today. And so we're going to be sitting there for the next couple of weeks because solar conjunction's coming up tomorrow, or actually Wednesday. So tomorrow is Sol 216. The end of that solar conjunction starts. And so we'll be sitting here until October the 16th. Ready for Mars to pop out the other side and we can start the operations again. So after that, we'll basically back up and we can't go this way, it turns out. So we have to go back around this way. So we're going to follow our path back to the landing site and then go beyond that and go around to the other side and arrive at the delta somewhere probably around the middle of February, basically a year from the time that we landed out here at our landing site back in February of 2021. So that's the plan. So stay tuned. As soon as we come back from solar conjunction, we'll start epic drives going back across the surface of a new world, looking at things that no one's ever seen before, and arriving at our next phase of our mission, which is investigation of this delta, driving into the canyon. So it ought to be some pretty spectacular scenery. So with that, that's the end of the presentation. I just wanted to point out, here's the book that I will be it will be published in November the 2nd, or at least it'll be released to the bookstores November the 2nd, so keep an eye out for that. It's all about missions to Mars, a history of Mars exploration, and some of the things that I've done during participation in some of those missions over that time. And so with that, I'll stop and start taking questions.
Okay, thank you very much. And actually, I should say that you all might have recognized that in a lot of ways, New Mexico looks like Mars, or maybe Mars looks like New Mexico. And in fact, we have lots of Mars scientists here in New Mexico. And I think that may be because of it.
Yeah, the New Mexico really is like Mars. I always like to say Mars is like New Mexico, just more so. I mean, they're both semi-arid landscapes. The landscape on Mars that we see today is basically left over from this time when there was lots of water. And so it was semi-arid at that time. And so a lot of the landscape features are very similar. And of course, a lot of the geology, there are like lots of sediments and a lot of lava flows. So it's that's why it's so similar to mapping geology here in New Mexico. It's a very familiar location.
Okay, so we have lots of good questions. So let's get started. How advanced is the Perseverance rover compared to previous rovers?
Yeah, it's the Perseverance is very much obviously based on the heritage of the Curiosity rover that previously landed at Jezreel at Jezreel Crater, and it has many of the same capabilities, but a few more advanced capabilities, like that auto nav that allows us to drive those great distances. It also has upgrades to some of the instruments, like the mass cam of Curiosity is the Z cam of Perseverance, which has a zoomable function, so we can actually do telephoto images of distance. SuperCam, of course, has many capabilities beyond that, including, the ability to, it has a microphone and lots of other upgrades to its ability to do the laser zapping and understanding of rocks. And of course, we have some other technology demonstrations, the MOXIE, the oxygen production, and of course, the helicopter. But also the Rimfax ground penetrating radar is something we haven't had previously. And it's proving to be quite worthwhile in understanding the context of some of the locations that we've been to. So that's just a short snapshot. In addition to some of the instruments on the end of the arm that have been upgraded, have more microscopic capabilities than previous rovers. And so we're all set to basically look for fossils on Mars.
And how fast does the rover typically move?
Well, if we're doing one of these automated drives, that drive I showed you maybe took an hour or two, so it's it moves fairly slowly. It'd be like a nice walking pace. We don't drive pedal to the metal, or at least pedal to the metal in this case is like a walking pace.
How are they powered, both the rover and helicopter?
Yeah, of course, like Curiosity, Perseverance is powered by a radioisotope thermoelectric generator. So it's a small plutonium source that generates the electricity, which basically charges a battery that we then use to do all these activities. And so it's capable of lasting for many, many years in the future. The helicopter is actually solar powered, so it actually has a little battery. It gets charged by the sun. So its lifetime is obviously limited by the fact that along about February we'll be entering Martian winter, and so it probably can't survive much beyond that point. But it's basically a solar powered helicopter and a nuclear powered rover.
And kind of related, how long can Ingenuity fly?
Yeah, so that's kind of an interesting question. It turns out that the primary limit to the flying capability is the blades have to spin incredibly fast, like 2,000 RPM, several hundred times that of the typical Earth helicopter, because the air is quite thin. So they have to spin very fast to generate the lift. And that in turn uses a lot of power, obviously, but it also heats up the motor considerably. So long flights, really the limit to flying is heating of the motor, which is limited to maybe 90 seconds plus or minus. And also now that we're coming into the changes of season on Mars, the atmospheric density on Mars actually changes radically by about 30%. From summer to winter. And so as it gets lower density, the blades have to spin even faster, which of course consumes more power and heats up the motors even more. So that's kind of a limitation right now on how long we can fly. And then of course how far is just depending on how fast we're willing to fly on those overflights.
And any other additional challenges to drone flight on Mars?
Yeah, let's see. Any other challenges? Well, we don't like to fly in windy weather, so it's always scary when we take these movies of it and it's there's like a dust devil going on in the background. You wouldn't want to get caught in one of those, but not really. It's usually limited to 2 o'clock in the afternoon, which unfortunately is when dust devils are active, because that's when the air is most stable for that sort of flight, if not against the vertical convection. And other than that, it's really you're having the right atmospheric conditions to fly. It's we're pretty much at the limit for how fast the blades can spin and generate lift. And there's a limit on the actual scalability of the whole process. So it's going to take some technology improvement to go to bigger helicopters in the future. But at least we're exploring, the envelope of flight on Mars.
Yeah, because this Ingenuity is only 4 pounds.
Yeah,
Right?
it's a little tissue box size body with a 4 foot, rotor blades.
So, speaking of dust devils, how do you prevent dust from fouling the camera lenses and other instruments?
Yeah, well, it turns out that dust doesn't cling to anything other than horizontal surfaces too much. So, I mean, your windows don't get nearly as dusty as, like, the hood of your car on a typical day sitting outside. And it's, the dust just doesn't stick. And even though, even here on the Earth, however, dust does stick to windows. And that's because of the moisture content, which tends to affix it to surfaces. On Mars, it's so dry, the dust, has no capability of sticking really. And it eventually, if it even it does coat a lens, it usually falls off.
But what about the sample tubes? Will they get buried by blowing sand over the years?
Yeah, well, we hope they aren't there that long. These dunes don't move that much and accumulate that much. But even if they did, it's been demonstrated with the test here on the Earth that we will be able to find them uh, if they are buried, because we will have very detailed information about their location. And the rover that's going to go pick them up has a lot of autonomy and capability of identifying these. So yeah, that's really not a problem. In fact, the samples are so well sealed, they're impervious in the environment. So they'll be quite safe for many years to come.
What is the role of AI tech in these missions?
Yeah, it's like, the main thing. It's like when we landed, that lander, that hovering crane actually had considerable autonomy. And it was actually literally checking the air photos of the landing area in real time as it was landing, looking for a correlation between what it was seeing and where we had previously identified good, safe places. And so that was like, a game changer, because that meant we could actually send the lander to a place that was actually absolutely safe. And of course, then the rover itself now has this auto nav capability. It's capable of, just basically deciding, what's safe to drive over and what isn't. And it doesn't have to stop and wait for us to tell it what to do. It does its own thing. So a lot of autonomy in this mission. And so it's going to be very important in the future, because the communication time with Mars is so long that if you have to wait until the end of the day and you get a transmission from Mars and respond to it, it's another day. And so it'd be much better if these robots can actually handle situations on their own. So that's what we're doing with this. That's another one of the technology tests.
And how does that actually work? How does the rover or the helicopter actually navigate?
Yeah, pretty much the same way you do. They
They know
basically,
where they are.
yeah, we tell it, where it needs to be. It has basically onboard, storage of these locations that we're telling it to go to, and it looks for the characteristics at that location, and it finds that those characteristics, then it correlates and gets a really high correlation between what it's seeing and what it's supposed to be seeing. And so it's really all about just having the air photo in one hand, and you want to go to a point and you actually walk until you start seeing the things that are supposed to be at that point. So that's literally what the helicopter and the rover are doing.
What are the processes that have caused the rocks to break off various outcrops, formations?
Yeah, pretty much the same thing as here on the Earth. Basically, it's just various types of mechanical erosion. It's you get to a point where the rock is basically not supported as the wind or whatever other erosion is taking place. It undermines a rock mass. And of course, rocks are all so fractured that they're not really connected to the rest of the rocks very well. So you just basically undermine it and it basically breaks away. So that's the most common characteristic. And so with time, it's a very slow process, but with time you generate these rocky escarpments, pretty much the same way we do here in New Mexico. For instance, the Petroglyph National Monument, you see all these rocks at the base of the lava flows, and it's the same thing is happening, just much quicker here on the Earth than it is on Mars.
So there's definitely evidence of weathering, physical and water.
Yeah, we certainly have evidence for wind abrading rocks. I mean, that's very common characteristic. In fact, a lot of the features we see are oftentimes ascribed to wind abrasion, even in basaltic rocks. You can see that here in New Mexico, by the way, a lot. And the weathering also is from very ancient times on Mars. Mars was a really wet place in the first billion years or so. In fact, it was soaking wet. And a lot of those, those really rotten rocks, those corroded looking rocks that we were seeing, those were, we believe, basically, underwater or, soaking with water in a ground table or something for a long period of time. And a lot of the minerals and salts and acids of groundwater basically leached into them and basically pulled apart the minerals, changed the minerals to clays and things like that. So just like it does here on the Earth for deeply weathered terrains.
This is an interesting one. How much you distinguish between volcanic and sedimentary?
Yeah, well, that's an interesting debate. We've been sort of having that on the mission because, again, it turns out that humans are really good at identifying things we're familiar with, and things that we aren't familiar with, we kind of don't even see them. And we have a lot of sedimentologists, and every rock they look at looks like a sediment to them. And meanwhile, those of us who are more igneous geologists, we see every rock we see, it's totally consistent with lots of the characteristics of igneous rocks. So it's kind of like this debate always going on. And you'd say, well, gee, all you have to do is pick the rock up and look at it and you can identify, well, it turns out that's kind of difficult, especially remotely, but also even if sometimes people bring rocks into the museum for us to identify. And sometimes I have a hard time because you have to kind of know what the context of the rock is to really kind of understand, kind of a starting point. Otherwise, there are all sorts of textures that look very similar in the two different types of rocks without some really detailed analysis, looking at a thin section of the rock under a microscope, that sort of thing, especially when they're really fine grained. So it's really hard to do. And so ultimately, what it'll come down to is getting those samples back. And it'll be a little bit more obvious, but also that's why I'm doing this geologic context mapping. So once we understand that, the context is a lava flow, for God's sakes, then it's likely that the rock that we collected from a lava flow is a piece of, volcanic rock. And so on. So that's part of the the whole picture. So it's kind of introduced a whole so this philosophical question about how you actually do geologic understanding of a location. It's actually trickier than you might think from here on the Earth, where you already kind of know the answer when you go into an area in a place where you've never been. It's kind of tricky.
Any evidence of lake sediments yet?
Yeah, well, according to the sedimentologist, yes, they're all over the place, but no, not really. Nothing that really to write home about yet. But maybe we'll see some later on. Maybe we're seeing it now in some of these strange deposits, but we'll kind of come to that conclusion over the next many months as we analyze more of the data we're getting back and as we do more of the traversing. gathering context about this site.
Okay. Naming the features on Mars. Isn't Zeta a Navajo word?
Yep, that's a Navajo word. So it turns out that for on these missions you name local features and areas and rocks and things. And so for this mission, we decided to use as our naming themes the names of quadrangles that we did of the area prior to landing. So they were broken up into these little rectangles. Each one has a name, and the particular quad that we landed in for the landing site was called Canyon de Chelly. And so for all the rocks in that map area, we named things using Navajo names. We got permission from the Navajo Nation to use certain names, and so they're on our list, and we've selected from those. And Seta, of course, is a name that we picked for that Badlands out to the northwest. And so subsequently, we've moved into another quad to the west of that landing site quad. And it's a quad French locality somewhere, I think, in the, I've forgotten the southern France. And so we've had all these strange French names, some of which are, even according to the French, are hard to pronounce. So you'll be seeing lots of French names. I think the current site, we just looked at a rock called Garde, and our first successful sample was one called Rochette. And yeah, so we have naming themes based on quads, so hopefully we'll get to one that everyone can pronounce before too long.
Does the rover turn around to go backwards, back down hills, or can it drive back in reverse?
Yeah, it can drive any direction. So yeah, we haven't had to do that yet. So I'm not sure what the rover driver's preferred method for that would be, but it depends on how far it is and what we're trying to do. It can it has these has cams that look out into the front and to the back, so we can drive back as well as forward.
Okay, and Mars gravity, what is it relative to Earth? And what weather phenomenon causes the dust storms?
Yeah, the gravity is like 38% of Earth, so I mean it's you would weigh a lot less on Mars, and it's fairly, but it's it's a significant amount of gravity because Mars is about half the size of the Earth, so it's it's less than the Earth, but more than the Moon, but it's good gravity for especially for flying in, because we don't have to generate so much lift. And what causes the dust devils? It's basically just like here in New Mexico. You see a dust devil, they're always like 2 o'clock in the afternoon, plus or minus an hour or so. And it's the ground being heated up by the sun, which is really warmed up by 2 o'clock, and the sun's still intense. And so the ground gets really warm, and so you get this convection. That is, the hot air is just kind of coming off the ground, and it turns into these swirls that pick up dust and create dust devils. So it's just like New Mexico again, just more so.
Does the helicopter possess the ability to deal with a dust devil during flight?
Yeah, we haven't had to experience that yet. In theory, it should be okay because the winds on Mars aren't that powerful, although the dust devils can be quite rapid winds. And of course, we are a lightweight vehicle, so we could probably fly in a dust devil, but the helicopter would be challenged to stay stable. It would immediately sense that sort of thing. It would probably seek to abort the flight and land if it started really having trouble like that. But yeah, it would buffet it around a lot, but it could fly through it probably.
What about Martian winds moving the core samples around?
No, it won't happen because the Mars winds, even blowing, screaming at 100 kilometers an hour, would be like a gentle breeze. And these are, significant little tubes laying on the surface, so they won't move around, and they certainly won't move far if they did.
Okay. And we did have a comment from one of our colleagues, a fellow Mars scientist, Dr. Horton Newsom from UNM.
Hey, Hort.
And he is on Curiosity. He says, and this is a great piece of information, the solar panels for the helicopter were made right here in Albuquerque.
Yeah, Sandia Labs especially has been involved in, development of hardware and some of the other capabilities for a lot of these missions. And so, yeah, the we're a solar powered state. So it's only natural that we should, build solar panels for Mars helicopters.
So based on the information we've collected from rovers, do we have a spot planned for landing humans?
No, there's, ongoing discussions about where to do that. And yes, it's too early to say. I mean, landing of humans on Mars is, well, as I discuss in the book, it's probably a couple of decades away. Let's put it that way. It's always 20 years from the present, whatever that is. But there's other issues that have to be resolved before that. So I predict it's going to be 2050.
Would the ground penetrating radar be able to detect subsurface water ice if it were encountered?
Oh yeah. Yeah, because water is, like I said, one of the characteristics of ground penetrating radar is that it's really influenced by the moisture content of the substrate. And so if there's any water down there, it'll, be like a major reflector. And that includes ice. So yeah, that's one of the goals. In fact, the Chinese rover Zhurong has a ground penetrating radar, and one of its goals was to actually look for subsurface ice as it drove along. So yeah, it can detect water and water ice very easily.
What is the cause of earthquakes on Mars or Marsquakes?
Yeah, there's several different types of causes. One is, small impacts that are still, happening off and on Mars. So we know that happens. Then there's things like rock falls. There's lots of escarpments and things on Mars, and periodically one of those lets go and makes a significant little local earthquake. We think that may have been one of the ones we saw over there in the Athabasca Fossae region. Really deep cracks in the ground. Although there's also the possibility there's other more volcanically related things going on. But more recently, this 4.2 was literally on the other side of the planet, which places it somewhere in the, the kind of the Valles Marineris, the Grand Canyons of Mars area. So maybe that was either, another big landslide or maybe something more deep-seated going on over there. So all the usual reasons that we have here on the Earth.
Is there a deep drilling experiment to extract samples?
Yeah, well, the drill coring capability on the rover actually penetrates, many centimeters into a rock. So that's about as deep as we're getting right now. But yeah, in the future, there's hopes, to have drills that can go down at least a couple of meters. That'll be particularly useful in places where we think there might be ice in the subsurface, a few meters. And but right on this rover, the drill core is drilling as deeply as we want to go.
Do we know the age of some of the rocks that have been sampled so far? Can we speculate about their sequence in geologic processes or about the sequence of processes that created them.
Yeah, of course, that's part of our big traverse that we're undertaking is to understand that sequence here on the crater floor. And we think, we think the delta is fairly old, and the crater floor was covered by something, lava flows, maybe other lake sediments or something. And so we think we have a good geologic sequence, but the age, probably, the delta is 3.8 billion years old or something, and then everything in the next few 100 million years would include, the lava flows on the crater floor and things like that. So we'll be able to see it with dating if we get samples from each of these units. So that's kind of why we're spending all of this time and effort trying to get a handle on some of these units that we suspect are younger than the delta itself. So at least if something goes wrong, we can't get those samples from the delta, at least we'll be able to say, well, the delta can't be any younger than these rocks that cover the crater floor. So we know we've got 2 good samples on board the rover now. So we just need to collect 36 more or something.
We are getting low on time here, and we have lots of good questions still. So any questions that we aren't able to answer right now in person will be answered by text later on. Let's see, just a couple more questions. Are you working on Mars time or Earth time, given that Mars time is so different?
Yeah, like I said, it's like almost coming on to 8 o'clock at night on Mars right now. So, yeah, we, for the first 3 months, we were on Mars time. And, that gets old real quick because it's just so out of sync, and especially since the mission's basically being operated remotely now. So we're not all on site where we can kind of be sequestered against the outside world. And so we went off of Mars time way back in May. And so we're on Earth time right now, and we're just doing the same thing that we did with previous rovers, which is sometimes you can plan the day just before it happens on Mars, and sometimes you need to kind of plan a couple of days because you're so badly in sync with Mars, like by 12 hours or something. You can't get the data in time to plan for tomorrow, and so we're doing that sort of thing right now. But the hours are really long, though. I think it's like 14-hour days for some of the operations people, and it's and some of the meetings move around all over the map. Sometimes they're in the morning, sometimes afternoon. In fact, you have to have a spreadsheet to keep track of all of these meetings and all of the things that are happening and when to plug in to attend a meeting. So I sometimes refer to the whole mission as being kind of exploring Mars by spreadsheet.
And I know you discussed this early on, but we had some latecomers. How will the samples get back to Earth?
Yeah, that's a rover goes, retrieves them, puts them on board an ascent vehicle, goes into orbit, rendezvous with an Earth return vehicle, and then it basically gets shot back towards the Earth. And basically, I think they go into orbit where they're retrieved in orbit, is the current plan. And so that's how they get back. I mean, it's going to be somewhere towards the end of this decade, hopefully. And
is there a plan to quarantine them?
Yeah, it'll be all the usual precautions. The capabilities for quarantining and isolating the samples are even way advanced beyond what we had for the initial lunar samples way back in the 70s. And so these samples will be, you can be assured they won't come in contact with the Earth environment for a long time to come. So we'll be investigating those in totally sealed environments. The tubes themselves are totally sealed against, the Earth's atmosphere. So you could probably take one out and handle it and not contaminate the sample, but they won't be handled because we don't even want to put Earth germs on the outside of the tube. So it's more of a question of the Earth contaminating the samples rather than the samples contaminating the Earth at this point. But we'll play it both ways when they come back.
Okay, and just two more quick questions. Let's see, where was the one? Documenting the samples. How do you actually know where an absolute location is relative to the photographs?
Absolute location, presumably, of the sample, the drill core. I mean, well, that's part of what the
Or
GXM.
the photograph itself?
Well, we take pictures of where we drill into the rock, and so there's the drill core in this rock, and so we know where that rock is in our greater panorama or location on Mars because we know where we are on Mars. So we can literally identify where that rock, that sample came from down to the millimeter on the surface of Mars.
And how long can Perseverance last?
Yeah, again, it's nuclear powered, so Curiosity is still going, right? It's landed in 2012, and it's got many years left to go. So we're talking many years, probably outlive its utility after we've sent many other exciting missions to Mars.
Okay, great. I wish we had more time. There's still lots of good questions, but as I said, we can add these answers in, I believe, to the chat or send answers to those folks who have asked the questions. So please join me in thanking Larry for a great talk, and keep checking your email and the museum website about future events and about the book signing in December. Thank you very much.
Yeah, you need a copy of this book. You know you do. Thank you for attending.
Thank you very much for being here.